So I'm going to get through this pretty quickly. I probably have an hour presentation. I'm going to try to condense that down into less than 30 minutes, if you'll permit me to go through some of these pretty quickly, but I'll try to get to the main points. And if you want the slides, we can negotiate later. So why do our companies care about our jobs? Well, we're in it to make money. There's a business objective. And oftentimes it's to operate our plants safely and reliably and responsibly. And a fundamental requirement, as you guys all know, is to control that manufacturing process. And nobody really cares about the enabling technology, except that it's a means to an end. And that includes the analyzers, and I'll talk a little bit about that today. So it's all about the money. I've shared this before, but this is a reality tree based on Pratt's theory of constraints. And if you think about what is your primary objective, it's to make money. Well, how can you do that? One of the ways that you can do that is to lower your costs. So if you follow the branch on the right side of the tree here, you can say, okay, well, how can I lower my costs? Well, I can reduce the operating costs. Okay, well, how can I do that? Reduce the number of people, reduce the maintenance costs. And then finally, you come to the conclusion that as far as the intersection between that objective and the enabling technology, you can begin to build the relationship that tethers the benefits from these measurements to the company's goals. So as Joseph mentioned a moment ago, we have roughly 22,000 analyzers installed at Dow with a replacement asset base of about $1 billion. So if you ask our clients how important that investment is, I can promise you they're very, very keen on what we can do to keep those assets competitive. And in order to achieve that, oftentimes we have to think about, well, how do we compare to our competition? Because anybody with a big enough checkbook can buy a GC, they can buy an IR, right? So if everybody has access to the same technology, the same people, how do you win? And why you win is identifying the most valuable opportunities to optimize the process, but also doing it better and faster than the competition. So a lot of our time is spent inside of the Dow fence to try to understand what are those opportunities and where are the benefits. And I would submit to you that that's the rate limiting step in continuous improvement. It's not necessarily the technology, although it's a key component. It's also understanding where are the constraints in your objective to make money. And the other fact of life today is that the EPC firms, although they serve a great purpose for us, these are engineering, procurement, construction firms, they don't have the skills or the depth and the breadth of skills in analyzers to do that to the extent that our clients need it. And so oftentimes the burden is on us. And if you look at the history, the evolution of analyzers in the industry, a lot of those analyzers came from the chemical industry, or the refining industry. The GCs, for example, that came from Phillips Petroleum years ago. It became Applied Automation in Bartlesville, and now Siemens owns that. And there's many other examples like that. So necessity is the mother of invention. So I'm going to cover real quickly because we agreed to compress our time here, but I think you'll recognize these in your own companies, that there are basically three themes in the industry: operational excellence, capital efficiency, and life cycle management. That really is what everybody is doing. It's almost like communism, I think, in the petrochemical industry. So that just means doing more with less. We also have some other corporate initiatives in Dow. One of those is energy efficiency. So 70% of our operating cost is associated with energy consumption. And of course, increased reliability. And reliability inside of our company sometimes has become a religion, but people forget quickly that it's a means to an end. It's not, you can make your plants 99% reliable. It doesn't mean you're making money. So you have to choose wisely where you spend your time to improve that reliability. And online analyzers are part of that story. Because we have one of the barriers to improvement is we have a culture of fixing problems, not avoiding problems. So we get rewarded for being heroes. Marcus and I were talking about this yesterday. We get rewarded for being heroes and fixing a problem, where the guys that avoided the problem it's almost invisible. Nobody even knows that they avoided it because it didn't happen. And then less time and resources are spent on technology. So that's kind of where we are, kind of chicken and the egg. So what are the needs and challenges? Another really big challenge in our industry is the workforce. And so there's a trend for all of us to figure out how do we cope with that paradigm, because our management are not giving us permission to hire more people. In fact, they're challenging us to live with what we have and see if we can cope with that. Here are two examples. So on the left-hand side is a sample system. I couldn't tell you which process or which application that is, but lots of moving parts. Very complicated. It works really well when it's maintained, but somebody's got to walk by that thing and make sure that everything is working properly. And you'd be surprised how many times there's this ignorance is bliss. They don't know that the thing is not working. They get a number out of the analyzer, and they're fat, dumb, and happy. You go out there and discover, well, there's no flow. And if you had a smart sample system that had the diagnostics, you would know that there was no flow, and somebody would take action based on that information. So that's the trend in the industry today, is to move away from dumber devices to smarter devices, automated self-diagnostics, so that you have some credibility in your numbers and you can trust the data. And trust means usually that analyzer is providing useful data to operations more than 99% of the time. If I asked you if your car didn't start one day out of the year, right, you would probably say, well, and that's like 1 out of 365 days of the year, you would say it's a piece of junk, right? You'd probably take it back to the dealer and say, hey, this thing is not starting, I want my money back. And online analyzers are even more so. And it's amazing to me how much we're willing to tolerate that unreliability. So here's a picture of two pictures back in the 90s. Analyzer shelters. These were very well-designed, climate-controlled shelters. The one on the right is a bank of GCs in a hydrocarbons plant. Well-controlled, worked really well. Well, that was in the 90s, and this was just earlier this year. So it really hasn't changed much in the last 30 years. And so, again, when we think about where do we need to drive the technology, this is a clue. And so I'll show a story in a moment, but just to kind of paint the target, I'm going to get through this really quickly, if you'll forgive me. We have, just to make the point, we have some mass spec and some Raman analyzers today, but maybe 1 or 2 or 3. I think we have like 3 online Raman in the entire company. That doesn't mean anything to most of you folks, but it's a high-end analyzer. Mass spec is even more high-end, very complicated. Compared to, say, FTIR, we have roughly 300 FTIRs. Again, these are high-end analyzers, information-rich, and people will install them, and they'll tolerate the high costs and the complexity because of the value that they deliver. But you won't install thousands of them. And then you get into things like GC, aluminum oxide, oscillating crystal. TDLs now are starting to take over, filter IRs. And we have hundreds of those. And then you get into things where we have thousands installed, pH conductivity. And so the question is, okay, why is that? Well, an obvious answer is that it doesn't take an army of people to maintain and install pH or conductivity. It would require an army of people to install and maintain mass spec, right? So there's a reason why we don't have thousands of mass spec, even though they're very information rich. Now, if I contrast that to pressure, temperature, and flow, right? You guys know this better than me. Dow, by comparison, I asked this of our instruments guys, said, how many pressure, temperature, and flow devices do we have installed? The answer he gave me was 700,000. That sounds low to me. I'm guessing it's more north of a million. And again, just to make the point, we have 22,000 analyzers, and in our industry, that's considered a big footprint. But we have more than 1 million pressure, temperature, and flow devices. So our clients want to use analyzers. They have a desire to use analyzers, but there's a barrier. And cost and complexity, the footprint, all these things that I have on this slide are those barriers. Here's one of the other drivers I think you all will resonate, is this concept of Industry 4.0. And you can look at all the value drivers for Industry 4.0. And I would say most of those intersect the objectives or the benefits of online analyzers, including optimization, predictive maintenance, you name it. And so there is a goal that's lined up between that vision and this enabling technology. But there's some things required to take us from where we are today to that vision. And some of those are reducing the cost and the complexity and customization. There was a time when we had our own instruments group. We would build these analyzers in our shop, build the electronics, the software, integrate all the components together, and install it ourselves. We don't do that anymore. We can't afford it, and the industry can't afford that. And we still have some of those legacy systems in the field today. It's amazing. So that's one driver. The other driver is keeping our assets competitive. A lot of our assets are near the end of their life, and one day will come when the analyzer doesn't work anymore, and our clients need to fix it. And sometimes the analyzer, you can't even buy it anymore. It doesn't exist. We started buying old computers off of eBay because the new computers are not compatible with the old software. And we'll pay a premium for those computers because, I hope I'm not telling anybody that owns those computers, we need those computers to keep that asset reliable. So keeping our tools competitive. I show this slide. Sometimes it upsets people that are in this list, but it applies to a lot of folks, not just these guys. But it's true that a lot of the technologies that we have today are very successful, but they really haven't changed much in the last 30 years or so. GCs, IR, there's a few examples. I think TDL is the most notable example change, but there's not many examples like that. So I can summarize what are some of our drivers, what are some of the key requirements for our analyzers. We need technologies that don't require expensive analyzer shelters. We need analyzers that have a faster speed of response. We need analyzers that don't require sample transport. If you could put a probe in the process and don't have to transport the sample, you've solved a lot of problems. Sometimes you've created some problems. It needs to be more reliable, lower maintenance, more standardization, and asset management support systems, having these in part of what we call a process analyzer resource management system, where the maintenance guys can look at that and say, yeah, this analyzer needs the filters plugged. We need to go out there and fix it. These are some of the ideas. We can drill down into some of the nuts and bolts here. So this is our vision of the future. Again, I showed you that slide of the modern analyzer shelter. Works really well, provides useful data to operations. They trust it, makes a lot of money for the company, but there's a limitation on how many of those that we can afford and how many we'll tolerate. And so there's a trend in the industry to move towards more field-mounted devices, things that don't require a great deal of support and demand on our time and resources. And this one that's shown on the right here is an in situ probe placed on a piece of fired equipment. And there's more and more of those coming out today. I want to make a point here is that it's not really a new concept to have field-mounted devices, right? That's been around quite a while. And one of the best examples I can think of are the shelterless GCs. I don't know if some of you are familiar with the old Daniels GC that they used in pipeline, liquid natural gas. And they have thousands of these things installed in the field, don't require an analyzer shelter, and very reliable, and they provide a lot of useful information to the client. But it hasn't enjoyed widespread success in the chemical industry. And there's been several products on the market that have, several companies that have developed their own version of the shelterless GC. And we have a few of those installed, but not many. And the vision there was that instead of having an expensive GC in a climate-controlled shelter, we would place this thing at the pipe and get the benefits of not having all that infrastructure, and even having a modular device where if something failed, you replace it with another one, and you're not doing field repair. And I had a lengthy debate with our clients about this. That there's still a psychological barrier to that paradigm. They're used to doing field repair, and if you're going to do field repair, especially in Texas, you want to have a nice climate-controlled shelter, especially when it's raining or there's mosquitoes or whatever out there, right? You want to have a place where you can perform the maintenance. That's a different mindset than having a device that's mounted at the pipe, and if it fails, you don't do repair in the field. You swap it out. And so there are some companies that are coming out with things like that. I won't mention the names, but you can look them up. But we tried this thought experiment. We built a cracker here earlier this year. It will be started up sometime in 2017. And we asked to get a bid from a company that sells shelterless GCs. And we chose not to do that. And I was very disappointed in that outcome, because here we've been clamoring for that kind of functionality, and yet we didn't make the decision. And so I asked the question, why didn't we make that decision? And part of it was because we didn't do our homework. We told the supplier what we wanted, but what we wanted and what we needed were two different things. We didn't clarify the goal very well. And one of the problems with the existing shelterless GCs is that they require distributed utilities. Well, in an analyzer shelter, you're bringing in all the utilities in one location. So you don't have to reproduce that utility at multiple points. You may have 100 or 120 GCs in a cracker, and if you're having to distribute all those utilities, you've just wiped out any cost savings you get from eliminating the analyzer shelter. So those are the kinds of things you have to think about when you define your goal. And so, here we are. Who do we blame? Do we blame the supplier because what they gave us doesn't meet our goal, or is it because, well, face it, you screwed up, you listened to us, right? So there's a fingerprint pointing contest there. So a good benchmark is the zirconium oxide sensor, right? This is something that can be mounted in the field without a PhD. It works. Now I know Don's going to look at me crazy and say, why are you still using Zerks? You shouldn't be using Zerks. And I agree with him, Don and Ryan too. But we have an answer for that, right? But it's a good standard. I mean, every car has 2 or 3 of these sensors installed on them. They work. They're very reliable in their application. They had some drawbacks, and we can talk about that. But as far as a goal, when this technology became available back in the 80s, it revolutionized combustion control. And I think our goal is similar in other applications besides oxygen. Here's an example. I think this is an e-book that I stole liberally from our friends at Yokogawa. Thank you, Joe and Ryan. That describes the benefits of this technology. It's interesting to me because maybe 5-7 years ago, there were very few suppliers in this market. There were a lot of suppliers that were selling into that. I mean, the first time I saw this technology was in environmental monitoring. They're using open path monitors to monitor fugitive emissions. And so you could monitor a large area of space in a short period of time at a low cost using these open path measurements, up to 1 kilometer or more path length. But nobody had discovered the benefit of applying this in the process industry. There were some examples in the power generation market, but today you go to most trade shows, and there's maybe a dozen suppliers out there today that are trying to jump into this market because they see the benefit. And one of the reasons is because it's a very reliable device. The laser source itself is telecom grade components. We're leveraging a mass market from telecommunications industry that just happens to overlap, fortunately, with some very important compounds in the industry. Oxygen is one of the most ubiquitous compounds in the chemical industry. Everybody wants to monitor oxygen. Everybody wants to monitor water. Everybody wants to monitor CO. So it's convenient that this technology is able to monitor those, and it can be mounted at the field and doesn't require an army of PhDs to maintain. We have hundreds of these installed at Dow, and they're slowly taking over a lot of applications that were traditionally paramagnetic analyzers, electrochemical, and others like that. One of the applications that we're interested in, we've co-developed with Yokogawa years ago, is combustion. And it lends itself very well because you can measure oxygen, which you need to run to do it safely, but also to measure CO, because CO is a very important compound in combustion because it's related to safety and efficiency. And if you're not measuring the constraint, you can't really optimize. So this has been one of the true success stories in our industry in the last 10 years. And it requires a lot of collaboration with companies like Yokogawa. So that's been a really fun project and great story. I'll go quickly through this, but the point I was trying to make a moment ago about what is the rate limiting step in developing a technology, and it's oftentimes the value proposition. If you think about it, if you're trying to ask somebody to do something different, you're asking them to make an improvement, what data do you need in order to drive that decision? And oftentimes, if you're just walking in there and say, well, it's better, they're just going to look at you, pat you on the head. I can't tell you how many times that's happened to me. So it's not a level playing field because there's already a built-in bias or prejudice against change. Nobody likes to change. And so in order to drive that decision, you had to have a credible, defensible argument to make the improvement. So my argument here is that what's really rate limiting in our improvement is not necessarily the technology itself. It's understanding what are the benefits and making that in a credible, defensible way. And continue. So the message here is that we can't sit back on our laurels and just wait for this stuff to come to us. We have to drive it and have to push it. So the next step change is here. I've just shared some of my ideas anyway of where we think the barriers are, where the paradigm changes are, and it's up to us to make those changes. So I really appreciate your time, and it was great fun meeting everybody.